Hi, this is Mrs. Jackson. This is Chapter 4 in Precalc CP. Chapter 4 is entirely about circles, and this is the very first video, Section 1, on the equations of circles. In this video, we're going to quickly derive the formula for the equation of a circle, either centered at the origin or at some other point on the coordinate plane. Okay, so let's get started. So key concept, a circle represents a set of all points that are a fixed distance, and that distance is r, and their fixed distance from the center of that circle, and the center is written as a pair of coordinates, and h is the placeholder for the x coordinate and k is the placeholder for the y coordinate, and r is the variable we use for the radius of the circle, and as I said, hk is the circle's center. Okay, we're going to first start out with a basic circle that is centered at the origin. So the origin, as you know, is 0, 0. And the radius, this radius here is like a hinge. If it rotated all around the circle, that r would be fixed or constant. And if we look at a point out here on the outside of the circle at some kind of coordinates, x and y, we can kind of drop a little line here perpendicularly so that we create a little right triangle. And so if you take a look at this x, if that x comes straight down here, then this side of the triangle would be, its length would be x. And here, if that's at a y coordinate, then the length of this side, or leg of the right triangle, would be y in length. So with a right triangle, we always kind of look at the Pythagorean Theorem, and the Pythagorean Theorem is c squared, or the hypotenuse, equals the sum of the squares of the two legs. And so if I do a little substitution here, I'm going to put in r for my hypotenuse, that's our radius, and I have the two sides. So there you have it. That is the standard form of a circle equation that's centered at the origin. In general, in textbooks, you'll usually see the x squared and the y squared on the left side. But anytime you see an equation where both the x and the y are squared, you're looking at the equation of a circle. All right, let's take a look at a real example here on the coordinate plane. We have a circle that's centered at the origin, and if you take a look at what that radius is, we're just going to read it right off the graph. In this case, r equals 4. And so if we wanted to write the equation of this circle, it's centered at the origin. We have x squared plus y squared equals 4 squared. And you can just simplify that 4 squared if you want to. More times than not, however, the circle is not centered at the origin. It's usually got a center somewhere on the coordinate plane. And so here we have a generalized diagram here where we are calling the center of this circle at these coordinates. H is our x coordinate and k is our y coordinate. And again, we've got some kind of point out here on the circle at placeholder values here, x and y. And so if this x here, if we drop that perpendicular line down to the center, if you will, or the line where the center interconnects, if that is value x here, then at this point will also be at x. And likewise, if we've got this center here at a y value of k, right, then this point here is also going to be at a y value of k. Okay, so if I look at these as leg lengths here, I'm trying to generalize here on what the two side lengths are. So if I look at this horizontal piece, I've got x here and h here. So the distance between those two is going to be x minus h. So that leg length is x minus h in length. And if I look at the vertical piece here, this top point is at y, and this bottom point is at k. So if I take a look at its length, I'm going to be y minus k in length. And because this is a right triangle, we are again going to use the Pythagorean theorem. And we've got c squared equals a squared plus b squared. I'm again going to put my radius in for my hypotenuse. This is our r. And the two sides have a variable expression associated with them. So this is the standard form of a circle equation whose center is located at h comma k. Generally in textbooks, again, you're going to see it written where the x's and y's are on the left. So you'll see it written this way. Notice that when h and k, they're up in quadrant 1 here, so they're both positive, but you're going to see that as a subtraction because we were getting the side lengths. So you'll see in some examples, if this is negative, that means h is actually a positive number. If this is plus, then that would mean your h is actually a negative number. So if we take a look at an example here, we have a center on this circle at 1 comma negative 2. So that's our center, h comma k. Looking around the circle, it looks like with this diagonal here, it would be kind of a lot of work to figure out what that radius is. So I'm going to look over here just horizontally or vertically, and I'm going to count what the radius is, and it looks like it is 4 units long. So I'm going to use my formula. We've got x minus h squared plus y minus k squared equals r squared. So for this particular circle, we've got x minus 1, and we have y minus a negative 2, so that turns into plus 2. And our radius is 4. 4 squared is 16. So that's writing the equation from a graph. I can also write the equations just given the center and the radius. So in this case, again, our center is hk, and our formula is x minus h squared plus y minus k squared equals r squared. So for this particular example, the equation would be x minus 5 squared, and we've got y minus a negative 3, so that's going to be y plus 3 squared, again equals 16. And this is the standard form, so you would just leave it in this form. And it's called the standard form because you could read the center and the radius right out of the equation. Okay, last example, we have x minus 0 squared plus y minus 1.5 squared equals the square root of 7 squared. X minus 0 is just x, so we can just simplify that, and we'll leave this other expression in the parentheses. Square root of 7 squared is 7. Okay, a couple more examples in writing the equation from graphs, and then we're going to go in the opposite. We're going to take the equation and then graph the circle. So here I have a circle. I'm going to try to find its center. So the center is at 1, 1. And again, that's hk. And I'm going to read the radius right off the graph if I can. And again, it looks like the radius is 4. So we've got x minus 1 squared plus y minus 1 squared equals 4 squared, or 16. Last example from a graph. I'm going to find my center here. And it is at negative 3, negative 1. And it looks like the radius is 3. So I'm going to write down my formula here. I've got x minus a negative 3, so that becomes a plus 3 squared. Y minus a negative 1 plus 1 equals 3 squared, or 9. Okay, going in the opposite direction, let's take a look at an equation and then graph So here we can read our center right here. We're at a center of 4. Because this is plus 2, that's going to be a -2 coordinate, and that is r squared. So our radius actually equals 5. So we're going to go to our center, and our center is at 4, -2. Here we are. And I'm going to look at a radius of 5. I'm going to count up and count down and go left and right. So I'm here and here. But in the case of a radius of 5, we can actually plot many more points than these 4 for accuracy. 5 is the hypotenuse length of a 3, 4, 5 right triangle. And so if you can imagine any right triangle in here whose sides are 3 and 4, that's going to give you a radius of 5. So for example, starting from the center, if I walk over 3 units and then up 4, that's going to give me a radius of 5 as well. Likewise, if I walk over 4 units and up 3, that's going to be right on the circle as well. So consequently, if you have a Pythagorean triple, then I think you can get a total of 12 points of accuracy here. So 1, 2, 3, be there. 1, 2, 3, be here, and so on and so forth. You'll have complete symmetry. 1, 2, 3, 1, 2, 3, 4, 4, and 3. And so without a compass, when you have this many points of accuracy, you can really draw a very nice circle freehand. All right, last example, we have a center at 1, 0, because we do not have a number here, and r squared equals 13, so our r equals the square root of 13. So again, we're going to find that center at 1, 0, and the square root of 13, the square root of 9 is 3, the square root of 16 is 4, so square root of 13 is roughly in the middle or between 3 and 4, but rather than graph by approximation, I want you to actually find some exact points on the grid. So remember that radius is from the Pythagorean theorem. So if I said c equals the square root of a squared plus b squared, so what 2 numbers whose sum of the squares are going to give you 13, in other words? And with a little iteration, hopefully you can see that will be 3 squared plus 2 squared. So if I look at points whose legs are 3 and 2, any combination of 3 and 2, I can get a couple of points right on the grid. So what do I mean by that? From this center, if I go over 2 and up 3, that's going to be right on my circle, or over 3 and up 2. And symmetry, you're going to have everything symmetrical around that center. So, go left 2, down 3, left 3, down 2, left 3, up 2, left 2, up 3. And so we can get a fairly accurate circle drawn by putting some accurate points right on the grid. All right, last page in this video. These 2 problems up on the top, I'm going to skip just in the interest of time and shortening this video. But if you're trying to check to see if a point is actually on a particular circle, all you're going to do is substitute that x and that y into your equation and see if you have equality. So I'm going to skip this, but the answer to both of these are no. Neither one of these points are on their respective circles. Okay, last problem is important, and it is a problem where you want to write the equation of a circle. This time you're given the center again, but not the radius. You're provided with a point that's on the circle. So the first tendency might be to find the distance between the center and this point, and that would give you your radius. Absolutely valid approach, but it's actually a little bit easier to just write the standard equation of the circle and actually solve for the radius this way. So we've got y minus k squared equals r squared. I'm going to substitute in minus a negative 4 would be plus 4, y minus 11. And by that, we're given a point. So this is an x and that is a y. And we can substitute in those values for the x and y. So I'm going to put 5 in here, plus 4, and negative 1 equals r squared. So I've got 9 squared is 81, and negative 12 squared is positive 144. And the sum of these are 225. So our radius is going to be 15. But we weren't really asked for the radius. If we wanted to graph it, I guess we would like to know that. But we were asked for the equation. So you want to put it all together then and just write the equation of this circle. So we've got x plus 4 squared, y minus 11 squared equals 225, which is our r squared. All right, thanks for listening. Hope this helps.